to continue our discussions for this chapter, we need to figure out how this hybridization thing works using s and p orbitals and how that gives us specific molecular shapes. So if you only used 2p orbitals, you predict a bond angle that's not actually occurring, so we have to have a different explanation for how that works. What we do is describe this in terms of hybridization of orbitals. In other words, there's going to be a hybridization of the valence electrons for nitrogen, and its valence electrons are 2s2, 2p3, 5 electrons. And the orbitals that are hybridizing are the single s and 3p orbitals. And if we hybridize them all together, they're going to become equivalent. So what we do, and this is a hypothetical thing, and it's done with mathematical calculations, but hypothetical atomic orbitals are going to be hybrids that are obtained when you get two or more non-equivalent orbitals from the same atom to combine, allowing to form covalent bonds. Well, how does that work? So if you take one of the s orbitals with three p's and you hybridize them together. So the consequence is that now we can imagine putting these together and making them come out somehow that's equivalent. In other words, the electrons have to be as far apart from each other as possible, the way we predicted in VSEPR. And we call this hybrid sp3 because there's one s and three p's combining to give us a hybrid orbital that's neither s nor p, but has a little component of each. So sp3 is 4 equivalent hybrid orbitals, and from this nitrogen example, it's going to be 3 of them that have unpaired electrons able to make a bond, and 1 of these orbitals is going to have a lone pair, influencing the overall shape of the molecule and more consistent with what we understand. So in the case of the ammonia molecule, the 4 equivalent sp3 hybrid orbitals, 3 have unpaired electrons that will bond with hydrogen atoms in the single s orbitals that hydrogen has, and 1 is a lone pair. These give us tetrahedral electron cloud geometry and the overall shape of the ammonia molecule being the trigonal pyramid. So this is consistent with the tetrahedral electron geometry being closer to 109. In other words, 107 is a little bit distorted because of lone pairs, and we call that trigonal pyramidal shape. The ammonia molecule is an example that is explained by sp3 hybridized orbitals to give us the expected geometry known to make sense for ammonia. Another example of hybridization explains the bonding in methane, CH4. Methane, as we can recall from electron configurations, has 1s2, 2s2, and 2p2 for its ground state electron configuration. And using the energy diagram at the left, where s has a lesser energy than 1s is less than 2s, which is less than 2p. The unpaired electrons are the ones we would expect should be sharing with the neighboring atom to make bonds. But there's 4 bonds being formed in methane. And so what we have to do is we have to assume that carbon is going to take on something of an excited state electron configuration so that one of the 2s electrons gets promoted, as we describe it, to a higher energy state in the 2p subshell instead. And so the consequence, now we have 4 valence electrons, all of which are unpaired, and that makes more sense in terms of trying to make 4 bonds. Well, if we had those things come together, does it make sense with the geometry that we know to be reasonable for methane? Well, if we take those 3 2p non-equivalent orbitals and hybridize them with the 1 2s orbital, we can get, again, sp3 hybrid orbitals, 4 equivalent orbitals that are somewhere in between the 2 in terms of energy and character, and the sp3 hybridized configuration means that those sp3 hybrid orbitals are all the same, 1 electron in each, and if you make bonds from carbon to hydrogen with each of them, the geometry should come out with equal angles all the way around, resulting in what we call tetrahedral geometry. So 4 equivalent orbitals result when they're hybridized. So as shown from the diagram here, the s orbital is spherical. The two p orbitals of three types are on different axes of the three-dimensional coordinates, and they have lobes that are two different types, and so they're two different colors. And you take those when you hybridize them and you can merge them all. They're all different, and they all merge together to make four equivalent sp3 hybrid orbitals. The four large lobes are oriented towards the four corners of the tetrahedron with the angles that we expect to be 109.5. The large lobes are shown in green. The small lobes are not obvious because they don't make sense. You can't really show them in this kind of a diagram. So this is a way of explaining the bonding in methane. Another way of thinking about hybrid orbitals is like taking liquids with different dyes in them, and they have different colors. So if you took one beaker with a volume of red dye combined with the similar volume 3 times of 3 beakers of a blue dye, you would end up with something purple. It's got a little bit of the component of the red as well as the blue, but it's neither red nor blue. And you could still divide it into 4 different beakers of the same volume. One way of making analogy for hybrid orbitals. So when you put that all together for the methane molecule, the 4 sp3 hybrid orbitals on carbon, shown at the left, can combine with the 4 hydrogens with their single 1s atomic orbitals, and then you make bonds between the carbons and the hydrogens, resulting from head-on overlap of the singly occupied hybrid orbitals that we describe as sp3, and that makes 4 single bonds with tetrahedral geometry. That will conclude my discussion of hybrid orbitals for this recording. I hope it helps you on your homework. I'll see you in class.